It's great to be here. So what I want to talk about today is the following. I'm going to take a step back. Now, one of the things that we know is that most stars form in clusters. So that leads us to the obvious question, namely, if stars form in clusters, why do they care if they form in clusters? So more specifically, what I'm going to talk about is how did the initial cluster environment affect the formation of stars and planets? And as you'll see shortly, I'm going to narrow that focus down to the question of how the cluster environment affects the formation of planetary systems. The reason being that the immediate cluster environment has more effect on the planetary systems than the star formation process itself. Then the second thing I'm going to talk about at the end is this question, namely if you can figure out how a cluster will affect the formation of a planetary system. It turns out that we live in a planetary system. So you can ask the obvious question, namely, what, if anything, can we say about the birth environment of our own solar system? Now, before I get into this, let me come clean and say that the first half of the talk is going to be a whole lot more rigorous than the second half of the talk. For the first half of the talk, what I'm going to do is I'm going to construct for you some, I'm going to try to construct for you with honest calculation some distributions of various effects that affect planetary systems. And you can see already that's a little bit dry. For the second part, I want to put all those pieces together and play basically CSI solar system and figure out what we can do about saying where our own solar system formed. And in doing that, each one of you will have an immediate objection to the way I do it because there's a lot of uncertainty that creeps into the discussion there. So that should give us a lot to talk about later. So my first point is to make this point of timescales. I think we all agree, in this room anyway, that the infall collapse time for an actual star formation event is 0.1 or maybe 0.2 million years, about 10 to the 5 years. And that happens for low mass stars and high mass stars. However, the clusters remain embedded or identifiable as embedded clusters for 3 to 10 million years. Circumstellar disks live for 3 to 10 million years. Of course, only about 10% of them live this long. Most of them are gone by then. And the time it takes to form a giant planet, not coincidentally, is also 3 to 10 million years. So it's this 3 to 10 million year time scale that I'm going to focus on today. So what kind of clusters am I going to consider? Well, we have various observations that measure all of the clusters in the solar neighborhood, and that's Lada, and Porus et al. And they give us basically a distribution of cluster sizes. So the number of clusters as a function of the number of stars in the cluster is 1 over n squared. This same law turns out to hold for bigger clusters, but the sample is completely different because we can only look at the bigger clusters farther away. So most people assume that those two distributions, the one measured locally and the one measured far away, actually match up. There's actually no a priori reason why the normalization should be the same, but that's what everybody assumes. So that when I need a probability, that's what I'm going to assume today, but it's important that I come clean on that assumption. So what effects are we going to put on the table today? In other words, what can a cluster do to a solar system? Well, there's really 3 classes of interactions. There's dynamics, there's radiation, and then there's particles. So where particles can include cosmic rays, which give ionization, and radioactive nuclei, which are a diagnostic in our own solar system's meteorites. So let me begin by, make the argument that the cluster actually affects the planet formation process more than the star formation process. And the reason is actually quite simple. It's one of velocities and timescales. We see the cores, the ammonia cores or the subcondensations that are forming individual star-forming events. They're moving at typical speeds of half the sound speed, about 0.1 kilometers per second. And the time it takes for the infall collapse to occur is about 0.1 million years. So if you just multiply those two numbers together, you get 0.01 parsecs. In other words, during the time it takes a protostar to collapse and form and gain most of its mass, it moves 1/100th of a parsec. My point is simply that when you move 1/100th of a parsec across a cluster that's a parsec in size, you don't have that many dynamical encounters. You just don't. So there's very little dynamics that happens during that phase. Similarly, the class 1 sources and class 0 sources are so deeply embedded that the external radiation fields have little effect. So for both of those reasons, during the actual infall collapse time when you make a star, there's relatively little cluster effect. After the star disk system has been made, it will then move at a few kilometers per second, because it will move ballistically through the cluster, and it will do so for of order 10 million years. So you have a couple orders of magnitude more effect, really. I should also say that in parsing the problem this way, I've ignored the actual formation of the cores themselves in the cluster. So the cluster might actually have an effect on producing those initial conditions, but that's not what I'm going to focus on today. So the first thing I want to do is I want to calculate the rate of dynamical interactions in clusters. And since I only have so much time, I'm going to just outline the calculation and not give you all the detail. So to cut a long story short, I have a student, or had a student, she's now graduated, she set up cluster simulations, and the short answer is she set up the clusters to be as much like the observed clusters as possible, with the observed cluster numbers, cluster radii, distributions of cluster stars, and distributions of cluster gas. And then she did n-body simulations to figure out how often a star would come by another star, or how often a solar system would go by another solar system. So this is all fairly straightforward. There's two important differences that you might not have thought about. One is that because of what I said earlier, that the clusters are moving at 0.1 kilometers per second, I mean, not the clusters, the cores are moving at 0.1 kilometers per second at the beginning. When you start out these simulations, you have to start out with the star disk systems having a subvirial initial condition. And that will actually increase the interaction rate. The second thing that you might not have thought about is that the types of clusters that we're talking about are typically clusters with 100 stars, 300 stars, 500 stars, something like that. So if you're doing the 500 body problem and you just run it once for 10 million years, you don't actually have enough statistics to give you a distribution of close encounters. So for each individual cluster you want to study, each choice of initial conditions, you have to run it 100 times. In other words, you have to run 100 equivalent versions of it to have enough statistics to give you the distribution of closest approaches that we seek. And here are the distribution of closest approaches. After all of that, so this is a whole thesis worth of work, which Eva did, I did not. You get a formula like this. So the encounter rate is some number, some base encounter rate, times the closest encounter distance to some power. So for any given cluster, the encounter rate is given by the value of big gamma and little gamma. If you had geometrical cross-sections with no gravitational focusing, little gamma would just be 2. What I'm going to show you is just the results of the main sort of 6 clusters in the middle of the parameter space. She has done far more, which I will not subject you to. But here I'm plotting the encounter rate versus distance of closest approach for clusters of 100, 300, and 1,000 stars with virial and subvirial initial conditions. The effect of the subvirial initial conditions is to make the stars fall deeper into the potential well, or become a denser system, and increase the encounter rate by a factor of about 4. You see that over this range of impact parameter or distance of closest approach we care, you get nice power laws. These are log-log plots in nice straight lines. And the answer to the question of what do clusters do is they let other stars come how close. And the answer is not, well, a number, it's a distribution. And the distribution has this form, but the values vary for each cluster that you put them in, okay? Now, having made the big point that the answer is a distribution and you get in trouble by trying to characterize a distribution by a single number, let me now try to characterize all of this by a single number, okay? So if you take all of the encounter rates that I show you here and you calculate what is the closest close approach that you get over 10 million years time, which is the time that the disks hang together, the time that the planets have to be made in, and the time that the clusters hang together, you get this value here, which is about 1,000 AU. So if you want to hang on to a single number, the closest close approach you get in this class of clusters is 1,000 AU. And of course, there's a distribution on that, as I've emphasized. Now, if you then ask, well, what does a 1,000 AU encounter do? Well, it will truncate disks down to about 300 AU, about a third of that value. So that's an effect. You will, in fact, truncate disks, because as we've seen, you can make disks larger than that. But we also make planets at 5 AU and 10 AU. so the disk truncation process will not completely drive or affect the formation of solar systems. The other thing it can do is that after you made the solar system, if the solar system remains in the cluster, then these encounters can jostle the solar system planets. Now, in order to answer that question, it's actually kind of an interesting calculation. Again, I don't have time to go through all the details, but let me just outline it. There's a lot of parameters involved. You have to set all the solar system parameters, all the binary parameters. It turns out that a good fraction of stars are binary, and binaries give you more bang for your buck in terms of encounters. So you have to set solar system parameters, binary parameters, and encounter parameters. And that gives you 10, 12, 13, or more, depending on how many planets you're considering as your base solar systems. So you could do Monte Carlo scattering simulations and calculate the cross-sections for various disruption events to occur. Now, unlike here in Michoacan, up in real Michigan, or the other Michigan, it's cold, the winters are long, so I have about 1 million of these simulations on my disk. And I can count through them and figure out what the different cross-sections are. But before I do that, let me give you a couple highlights. So you can do it with various solar systems. You can do it with like just one planet like Jupiter in a cluster setting. You can do it with Earth only in the field, and so on. And I will just show you a few highlights. Here's a typical one, which means it's the most interesting one we got. So if you have a Earth and Sun system interacting with a pair of binary red dwarfs, you get a nice resonant interaction where the red dwarf binary pair comes in, orbits around the Sun and Earth for a while, steals the Earth, or one of the binary pairs steals the Earth, which then ends up being given back to an orbit around the Sun, where it orbits a few times, and is then given back to the third star, the second member of the binary pair, which leaves with Earth in a habitable orbit. Now, what's cool, not that this is a very likely event, but what's cool is that through these kinds of calculations, you can calculate the odds of this happening. So the odds of Earth being ejected from our solar system during a 3 billion year window is about 1 part in 10 to the 5. The chance of Earth being captured through a system like this, or through an encounter like this, over that same 3 billion year window is about 1 part in 3 million. Again, these are very low probability events. They're probably not important for anything other than the fact that you can calculate them. Now, what we want to do, though, is not calculate this sort of a gee whiz slide, by the way, in case you didn't realize. What we want to do is we want to put this in a cluster setting and see how the clusters can sculpt solar systems. So this plot shows more what we're up against here. Here we start with solar systems that are analogs of our outer solar system. So I have a Jupiter analog, a Saturn analog, a Uranus analog, and a Neptune analog. They all have the masses of our planets and the semi-major axes of our planets, but they're started at exactly 0 eccentricity. The point being that it's easier to excite eccentricity than to damp it through these encounters. And then I'm going to plot the orbital elements of the planets post-encounter, and you see there's this explosion of orbital elements upward. So the net result is that it's very easy to excite orbital eccentricity through encounters. It's rather difficult to move semi-major axis through encounters. But through combining these, we can calculate cross-sections. So I can calculate the cross-section, we'll take a 1 solar mass star here, for each of the 4 planets. I can calculate the cross-section for increasing the eccentricity beyond a given value from 0.1 all the way to 1, where once I've increased the eccentricity to 0.1, I've ionized the system, the planet has escaped, and I can calculate, liberation cross-sections or ejection cross-sections. So for all of these plots, you can combine them, you can collapse them into one scaling cross-section for ejection, which has this value. This error bar here is not the Monte Carlo error bar, which is much smaller. It's only about 1%. This 10% error bar has to do with the degree to which all of these curves have the same shape. It's the degree to which similarity holds. And one of the things that you notice is that the ejection cross-section goes like 1 power of the semi-major axis instead of 2. That has to do with gravitational focusing, if that's not obvious. But we have a cross-section for ejection, so then you can put this in conjunction with the encounter rates that I showed you earlier, and you can ask a question like, in a given cluster, how many planets are ejected through dynamical interactions? Turns out the answer is 2. Or it's a couple, right? So we see lots, or we think we see, lots of freely floating planets in some clusters, but they're not produced by this effect because it doesn't work. The planets that you see freely floating in clusters are probably produced by planet-planet interactions within their own solar systems, not by external perturbations. Nonetheless, it's really easy. The cross-section for increasing eccentricity is much larger, right? And in our solar system, as you'll see, we have low eccentricity of our planets. So we know that our own solar system was not subjected to very close dynamical encounters, at least after we made our planets. So we have these cross-sections in hand. Another fun thing you can do is that in addition to planets, solar systems have lots of rocks. They tend to eject about 5% of their solids during the course of planet formation. So the number of rocks that are big enough to carry microbes is huge. And you can calculate the cross-section for those rocks to be captured by other solar systems. So in a cluster, it turns out that every solar system shares rocks with every other solar system. It's like kindergarten, right? Where every kid shares germs with every other child. So if our solar system developed life early, it has the possibility of infecting every other solar system in its birth cluster. But the bottom line is that the clusters have a relatively moderate effect on the solar systems through dynamics. Now, they can sculpt them. You can truncate the disks down to 300 AU. You can increase the eccentricity of the planets after you've made them, but you're not completely driving the process. So let's turn our attention now to radiation. So let me give you the summary first, and then I'll fill in some detail. So the way in which radiation matters most is it photoevaporates disks. And the radiation from the background cluster in a healthy cluster will often dominate the radiation from the star. Now, this is especially true in the outer disk where you're evaporating. This is far less true at 2 AU or 1 AU where Al Glassgold was working yesterday. It turns out that in this regime, the FUV radiation wins against other processes. And as I'll show you, a typical value of FUV flux is 3,000. This 3,000 is in units where 1 is the interstellar radiation field, and the interstellar radiation field is 1.6 times 10 to the minus 3 in CGS units. But this typical value will evaporate a disk around a solar mass star in 10 million years down to 36 AU, which is remarkably close to the orbit of Neptune. So that's kind of just a ballpark for where you are on this process. So if you ask the question, what's the typical FUV radiation field experienced by a forming solar system? It's this distribution. So let me just tell you in a few words how we got this distribution. You have to fold together 3 distributions to get this distribution. There's a distribution of clusters, which I showed you on one of the first slides. Then for each cluster, you have a number of stars. Then you have to sample the IMF that many times to get the actual masses of the stars. And then you have to calculate the luminosity, in this case FUV, for each of those stars. And then for each solar system in the cluster, you have to sample the radial positions of them to turn that luminosity into a flux. So you have to go through distribution of the clusters, IMF distribution, and distribution of positions, and you just count through that over and over and over again. So if you count through that billions and billions of times, you get a nice distribution. The actual distribution is a solid curve. A Gaussian plotted on top of it is the dash curve. So you see it's very Gaussian with a low tail. The values of 300, 3,000, and 30,000 are marked here. So you see that, again, 3,000 is in fact a typical number. Why did I choose those 3 values to mark? Because those are the 3 values that I've been able to calculate the photoevaporation rates. So let me step you through, again, very briefly, how you calculate photoevaporation rates in these systems. So what you have to do is you can have a star disk system, and FUV radiation heats up the disk. You can have flow off the top and bottom and flow off the edges. The edges dominate, so you can make a nearly spherical calculation from the flow from the outside, or from the outside edge outward, and you have to calculate the fluid fields as they wind through this or as they propagate outward, and the radiation is propagating inward. This is actually a fairly easy, or at least straightforward calculation if you knew the thermodynamics. You have to know the temperature of the gas at each point here. If you make an isothermal assumption, you can do this almost analytically. But the problem is that this is like a PDR region. So for a given density and column density, different chemical species come in and out of existence, and you get a lot of structure in the temperature curves. So these are the results of Dave Hollenbach's PDR code for the radiation fields of 30,000, 3,000, and 300, the ones I marked on the previous slide. And you see that for a given density, you get lots of bumps and wiggles in the temperature as a function of column density. And you might worry that these different bumps and wiggles will have an effect. The answer is they actually only have a small effect. So all those bumps and wiggles and those collapse to these little tiny wiggles here in the density and velocity fields for that flow. And that means that you can calculate the mass outflow rates, the evaporation rates, with some confidence. Now I'm going to plot them here as an evaporation timescale. So for the three radiation fields that I showed you, for a solar mass star, and for a disk that starts with a tenth as much mass as the star, I can calculate how far down you will evaporate the disk in as a function of time. And I've marked 10 million years because that's our sort of fiducial time scale for this talk. So you see that a radiation field at the low end of 300 does virtually nothing. A typical radiation field of 3000 will evaporate a disk down to 36, 35 AU, somewhere near Neptune. And a 30,000 radiation field will evaporate you down to about 15 AU, which is starting to eat into quite a bit of the disk. But you see that you can still make Jupiter almost in every case, which is an interesting result. Now you can ask, well, what about EUV? Well, you can play that same game for EUV. So this is the distribution for EUV. In different units, it has this peak value of 10 to the 12, and that's in units of photons per second per centimeter squared. The evaporation timescales for this is much more straightforward. They've been calculated previously by Hollenbach and Armitage and Clark and a number of others. So I'm just plotting them here. So for the 10 to the 12 peak, we only evaporate the disk down to about 300 AU in that same timescale. That's why FUV dominates EUV, at least generally. Of course, in the middle of Orion, that can be different. Not surprisingly, and I'm going to speed up a little bit here, not surprisingly, evaporation is more effective around smaller stars because the potential well is more shallow and the amount of disk mass you have to evaporate is smaller. And there's also disk accretion. So if you have the compromise between evaporating a disk from the outside due to the cluster evaporation and draining it on the inside due to accretion, it's hard to make the disk last longer than about 8 million years, which is roughly consistent with the disk lifetimes that we see. So the bottom line for the second part of the first half of the talk is that radiation dominates over dynamical effects in terms of how it sculpts solar systems in clusters. So to conclude the first half of the talk, let me just give you a few thoughts. We're in this sort of uncomfortable in-between region where clusters have a moderate effect on their solar systems. They do jostle the planets. They do affect the eccentricity. They do evaporate the disks. So you can't ignore the cluster effects. At the same time, they don't completely change the story. They're not the dominant, the external forces or effects that I'm talking about here do not completely change the paradigm of solar system formation. And because you're in this, and in addition to being in this in-between region, each effect that you ask, will I eject a planet, will I evaporate a disk, has to be drawn from a distribution. So the answer that I can give you in terms of figuring out what clusters do is to give you those distributions. So we have distributions of closest approaches. If you want an expectation value on that, you get about 1,000 AU. That will truncate disk dynamically down to about 300 AU, but they're truncated due to radiation at 30 or 40 AU. And the lifetimes are bounded from above at about 10 million years. We moderately alter the planetary orbits, but it's very rare to eject planets. Now, in addition to what I talked about already, there's a whole host of other things that clusters can do, but they're generally less important than the ones that I talked about. So in the interest of time, let me continue. let's ask this more fun question, namely, what can we do given all these distributions that we've now calculated, and I'd argue at least somewhat honestly, how can we put them together to put a constraint on our own solar system's birth environment? Now, of course, here, exactly what you put into the calculation will affect what you get out of it. So I've just changed gears here from what I consider honest calculation to, we'll say, fun calculation. So keep that in mind. One of the problems with the solar system is that we know way too much about it, right? So if you want to explain every aspect of the solar system, you'll never get there. So let me just put down 5 things we know about the solar system and then demand, one way or another, that the birth environment explain or be commensurate with these 5 properties. And then we'll see what we get. That's the game we're going to play now. So one of the properties of the solar system is that the meteorites suggest that when the rocks became rocks, there were live, short-lived radioactive species. That suggests some type of enrichment, some type of nuclear enrichment. We also see that the planets are well ordered. They have low eccentricities and low inclinations. And we've seen that it's easy to disrupt that. There's an edge of the solar system. There's actually 2 edges to the solar system. If you take the solar system today and reconstruct it, adding the gas back in, you see that there's a big power law slope down to about 30 AU where Neptune is. Then there's a big gap. But the surface density doesn't go quite to 0 at 30 AU. There's a bunch of rocks out there, which we call the Kuiper Belt. And that lower level of surface density continues for another 40, 50, maybe 60 AU. And then there's another precipitous drop. So there's 2 edges of the solar system. There's a gas edge at 30 AU, and there's a rocky edge at, let's say, 50 AU. And finally, there's this dwarf planet SEDNA, which has a crazy orbit. And we don't really care about SEDNA per se, but it's a bit of a barometer. It tells us something happened to give us SEDNA. And as I'll talk about in a minute, the most likely event that gave us SEDNA is some kind of close encounter, just the kind of things that happen in clusters. So what I want to do is I want to say, if our birth cluster explains these 5 properties of the solar system, big if, then what does that solar system environment look like? So here are the short-lived radioactive species. In the old days, which is before Frank, we focused on aluminum-26 and then some of the other radioactive species. And in order to explain the observed nuclear abundance, the best suite of abundances came for a 25 solar mass star, which is a pretty rare event. Now, since that time, there's 2 complications. One is that the X-wind can explain the aluminum-26, or at least mostly. There's beryllium discovered, which has to be produced by spallation, which means the X-wind almost certainly was operating, or something very much like it. On the other hand, we also discovered iron, and a lot of it. And iron can't be produced by spallation, so you still need a supernova.
That result seems to be going away.
What, the iron?
Iron, yeah.
Well, if you remove the constraint, you will actually not change my answer, as you'll see. Although you will remove that constraint. But let me come back to that. One requirement that you would require is that you have a 25 solar mass star blow up in the general vicinity of the solar system. The other thing that we see about our solar system is that it's well ordered. These are the eccentricities of the giant planets, and these are their inclinations. And the point is that they're small. So if I take the Monte Carlo scattering calculations that I discussed earlier and ask what's the cross-section? What's the cross-section for increasing the eccentricity of any of the planets, and Neptune's the easiest, above 0.1, which is twice the values I showed you on the previous slide, or increasing the relative inclination angles to being bigger than 3.5 degrees, which again is twice the range that I showed you on the previous slide. In other words, doubling the eccentricity and inclination angle of our solar system, the cross-section is 400 AU squared. Now, that's a relatively big cross-section. You'll notice it's actually much bigger than the geometric cross-section of the solar system, but that happens to be what it is. So, here's the first compromise. If you believe in iron, which LEAD is not, but if you do, and you want a birth cluster that has a 25 solar mass star, that pushes you to being in a big cluster because you're more likely to have a supernova with such a big star. If you want to not produce too much eccentricity or inclination in the giant planets, that pushes you to being in a small cluster because bigger clusters live longer and have more chances for encounters. So that gives you these two probability distributions. The probability of survival looks like this, the probability of having a supernova looks like this, and if you require both of them, you get the product of them, and that gives you an expectation value for the size of the birth environment of about 2,000. Now let's suppose that you want to explain the other effects. Well, the easiest way to explain SEDNA, in fact the only way that this long series of dynamicists have been able to explain SEDNA, is to have an encounter. And the encounter has to be between 400 and 800 AU. If you have an encounter at the lower end of this range, let's say 400 or 500 AU, with one encounter you can simultaneously explain the SEDNA orbit and sculpt the outer edge of the Kuiper belt to give you an edge in the rock disk at 50 AU. So we want an encounter, and we want an encounter of about 400 or 500 AU. The other thing we want is we want an edge of the gas disk at 30 AU or so, but not a lot less than that, otherwise we can't make the giant planets. So if you're in too big of a cluster, you'll have too much radiation, you'll get too much evaporation, and you won't have enough gas left to explain our solar system. So I'm going to add two more constraints to the plot, which is shown here. So here I have these requirement that I don't have too much scattering, so that I don't change the orbits of the giant planets too much. This dashed line is the requirement that I have enough scattering to give me SEDNA and the edge of the Kuiper belt. And then this is the supernova constraint again. So this is what I was alluding to earlier. If you don't believe in supernovae, if you do believe in Kuiper belts and SEDNA, you get exactly the same constraint in terms of what it requires for the birth environment. The radiation constraint is this curve, which isn't on this kind of argument that different from the survival constraint. So the addition of all of these constraints doesn't actually change the picture very much. You still get an expectation value of a few thousand stars. So there is a consistent scenario. If you form the solar system in a cluster of several thousand stars, there's a reasonable a priori probability of being in this range. You can get enrichment of short-lived radioactive species whether you need them or not. You can get them. And it will help with the aluminum-26 and other things, which just puts, it doesn't mean that the X-wind doesn't operate, it just means that it doesn't have as far to go. And then you can have the survival of the orbits that we see, but that same cluster will evaporate the disk down to about 30 AU, where we see the edge of the solar system. It will produce SEDNA, and it will truncate the Kuiper belt at 50 AU. So you can do all of these things sort of comfortably in a cluster in this sort of size range. And if you don't think too much more about it, that sounds pretty good. But since I have a few minutes left, right, I can tell you the things wrong with this argument. So the first thing is that if you want to have the supernova enrich the solar nebula, you have to be close enough to get enough iron. But you also have to be far enough away that you don't blow the disk apart. So here's this curve here is the one that matters. This is the stripping radius as a function of distance from the supernova. So we want the supernova, or the solar system, to survive beyond 30 AU. I can't be closer than about 0.1 parsecs from the supernova when it goes off. In order to get enough iron, I have to be within about 0.3 or maybe 0.4. So I kind of have to be in this box. So there's a non-zero part of parameter space, but there's only about a 10% chance that the solar system would be in this box when the supernova goes off. So 1 in 10 effects happen about 1 in 10 times, it turns out. But it's another 1 in 10 effect, right? So there's a whole bunch of these. That's the problem, right? So the 25 solar mass star that's going to blow up will live for 7.5 million years. So in order for the disk to still be around at 7.5 million years, the disk has to be fairly long-lived. Now, you've all seen this famous, there's various versions of the plot that Jesus Hernandez and many other folks have done that plot the disk lifetimes as a function of, or the disk fraction as a function of lifetime. Only about 10% of the disks are still around at this time. So there's another 10% effect. And the solar system can't actually be at 0.1 parsecs for all of the 10 million years, otherwise it will get too much radiation. So it has to live near the edge of the cluster, which is normal, but be a little bit closer at the time of the explosion, another 10% effect. It has to have a close encounter close enough to produce SEDNA, but not too close so as to disrupt the orbit of Neptune, another 10% effect. It must live in its birth cluster a pretty long time in order to actually have the SEDNA-producing encounter. It's another 10% effect. The Oort cloud has to be made later, and then there's other things that you'll come up with, like the orbits could be damped afterwards, and the planets can move around. And all of these things can be addressed, but they're starting to be low probability events. So if you put all these things together, you can even put in the fact the sun's actually a pretty massive star. That's a 12% effect. It's a pretty metal-rich star. That's a 25% effect. If you were just blindly to write these all down in a Drake equation and multiply them together, you would get the probability of producing the solar system is really, really small. So the question I have for you, something for you guys to fight about at lunch, is does this matter? Is this a problem? Well, no, I think it's something more subtle or more simple than that, right? What this is really saying is that suppose you multiply 10 things, each at 10%, you get 1 in a billion, right? That means your parameter space of possible solar systems subject to these properties has a billion answers, right? And we're sampling one of them. That's not a problem. There's 100 billion stars in the galaxy. But it could be 1 in a quadrillion. Would that be a problem? Well, not really. It just means that the total number of combinations that a solar system could have is more than the number that are sampled in our own galaxy. I mean, we actually see that every day. Every time you wake up and look in the mirror, the number of DNA combinations is far larger than the number of people on the planet. But that doesn't keep each and every one of you from having a particular DNA combination. So you have to be very careful what you do with these numbers. All I can do is calculate the 10% effects, or the probability that each one of these things will happen 1 in 10 times. How we put them together leads to lots of interesting fights, right?
But doesn't this mean that we shouldn't find another solar system? It's difficult to find another solar system.
Well, it's difficult to find another solar system that is exactly like ours. But suppose you find another solar system that's like ours, except that Neptune has twice the eccentricity. Most people would say that's pretty close. But the way we're doing the accounting here, that wouldn't be allowed because that's not our solar system. Or you find another solar system that doesn't have SEDNA. Well, life could evolve on Earth whether we had SEDNA or not, I'm pretty sure. We're just using those particular odd properties of our solar system as a way to dynamically constrain our past dynamical history. Now, I should remark that, as Lee pointed out, the abundances of all the nuclear species that I outlined are in fact subject to change and are continuing to be studied. There are, in addition, other ways to enrich things in nuclear processes other than a supernova. There's spallation sources, of which I think it's safe to say the X-wind model is the leading candidate. That can explain, and is necessary to explain, the beryllium. It can explain the aluminum-26. It, as I understand it, cannot explain the iron. AGB stars and Wolf-Rayet stars are basically supernovae without the explosion, in the sense that you can produce radioactive species in stellar nuclear synthetic processes. In this case, you get them out by winds. In this case, you also get them out by winds, I guess. But the probability of having them is lower. Matthew Gunnell has an interesting scenario where instead of having one supernova, you have a whole bunch of them, which seems less likely, but you do it in a previous generation, which, if you do the things right, makes it more likely, according to him, although there's some tuning involved. And then you don't have to have a 25 solar mass star necessarily. With the X-wind and other spallation enrichment, you can relax that one a little bit. So let's go back to our original questions, and then we'll wrap up. Our original questions were, how does the initial environment affect the formation of stars and planets? And second, what can we say about the birth environment of our own solar system? So to answer the first one, what we have done is we've tried to produce for you an honest calculation of all the distribution of effects. So we have distributions of closest approaches for solar systems passing by each other in clusters. We have distributions of EUV and FUV radiation, also have distributions of X-ray radiation now. We've calculated disk evaporation rates for FUV flux. Other authors have calculated disk evaporation rates for EUV flux, and other people yet have calculated disk evaporation rates for internal radiation fields. We've calculated cross-sections for solar systems to be disrupted in a variety of ways, and the cross-sections for rock capture. I've also spent a lot of time calculating orbits in these cluster potentials, but I haven't subjected you to that. So our conclusions are that the initial cluster environment has this moderate effect on planets and disks forming within them. The effects are important. They sculpt the solar systems, but they're neither dominant nor negligible. They're in this in-between range where it's difficult to actually even say exactly how important they are, because everything has to be couched in a convoluted statement of probability. But nonetheless, we have quantified these in terms of distributions. And then second, for fun, we have taken the distributions from the first part of the talk and tried to construct constraints on the birth environment of our own solar system. And when you do that, you find that you can explain pretty much all of the properties that we put down for our solar system with a cluster in this size range. And if you want to be a little conservative, you can expand it to this decade. So if you want to explain the properties, the 5 properties I set out to explain on our solar system, you need the birth cluster to be in the decade between 1,000 and, let's say, 10,000 stars. So this is a good place to stop, and I thank you for your patience.
Fred, do you have to worry at all about jets and collimated outflows that could rip, if you're unlucky enough to be in the path of a jet, will that sort of blow away the outer parts of the disk, or is just not important?
Oh, well, that's a good question. The honest answer is we have not taken that into account. So that jets and outflows could, in fact, have another class of influence on things in clusters. It's probably not going to dominate, but it should be looked at. So I would have to do some calculation before I give you a more precise answer.
Yeah, so this is a response to your request to ask about your orbit calculations. So the particular question I have is, in a cluster like Orion with a few thousand stars, does every star see the average G0 over the 10 million years? Or is there a large spread in the average G0 that individual stars will see?
That's a good question. The honest answer is we only have a partial answer to that because we don't have full kinematic data, right? So actually, so I can tell you a few things.
So what did you do?
Oh, well, we did a couple things. So one thing maybe is what Lee is hinting at. Is Lee and I had 2 students, John Tobin and Eva Proskow, who took the existing data for Orion and tried to see what kind of cluster potential you needed in order to explain the actual kinematics, right? And to cut a long story short here, what you need is that you need subvariable initial conditions for the orbits, which will affect them. You need the potential to be non-spherical, probably at least triaxial. And you have to have the observational viewing angle for Orion not down one of the triaxial axes. So the dynamics or the kinematics we see in Orion are complicated enough that you need at least those 3 properties, okay? Now, that also tells us that if you think about orbits, you can have orbits that are nearly circular or nearly radial or isotropic, right? So if you had isotropic orbits, and by isotropic or radial, I mean they're velocity ellipsoids, right? So if you have isotropic orbits in their velocity ellipsoids, and they last for many, many dynamical times, then you'll fully sample the G distribution. Okay, but you're kind of in, again, this never-never position, because you're only going to have tens of orbits, which is not enough to fully sample.
And you're assuming that all the stars begin outside of their molecular cores at the same time, right? You don't have the gas and stars coming out.
No, it's a little more complicated than that. We have a slightly more physical model than that. We have a model of a cluster with a gas potential and stars, and we prearrange where they're going to form at the beginning of the simulation. So we know one will form here and one will form here. But they don't all form at the same time. They form in a little window, delta t, which is taken to be either 1 million years or 2 million years. The gas stays in the cluster for either 3 or 4 or 5 million years. And then the whole cluster is integrated for 10 million years.
The thing is, so suppose the solar system was on a radial orbit, because that's what you would need to get it close enough, right? But most of the time it would spend it away. I mean, I'm just trying to understand when you calculate the...
You want to know...
Did you take into account whether the orbits were isotropic or circular or radial tangential or whatever?
Okay, well, there's several questions in there. Let me try to answer at least some of them. Okay, well, for the distribution that I showed you of FUV radiation, I just assumed that in any cluster, I'm just doing a spatial sample. So that in order to have the right density distribution of the stars in the cluster, I have a distribution of radial positions, and that lets me turn the luminosity of that into a flux. And that gives me that distribution. But then in another paper, what we did is we took the orbits, which are calculated in yet another paper, and we took those orbits and we averaged the flux over those orbits. And then we used more radial versions and more isotropic versions and more circular versions. And for anything reasonable that's not completely radial or completely circular, you get back the same distribution so that if I plotted it, you wouldn't be able to tell the difference, okay? Now to answer your other question, what I do for the disk photo evaporation is I choose a G, because I have to use that PDR model. And for that G, I give you an M dot. And for that M dot, I can give you a time scale. That's a simple transformation. So to apply that to a cluster, you have to assume that the solar system in question is experiencing that G of, let's say, 3,000, more or less for its whole lifetime. Now, the typical orbit in the typical solar system in the typical cluster will do that. But if you have something that's in a plunging radial orbit like a propelid, it will get blasted much more than that. And you could do that too, but that's not what I showed, right?